Okay, so for 6-3 notes here, we'll pick up with the beginning and go through. So review of some of what we've seen going back to Physics 1, and then we actually will see a lot of new material in sections 3, 4, and 5 here. So make sure you guys do follow along on these sections closely. And we see a lot of new calculus stuff, so if you do have trouble, come find me and let me know so I can help you through it. But anyway, the first couple slides, and really for the most part this first section, isn't too bad, but it is at least a few new relationships for us. But anyway, so how do we find the force of gravity exerted between two objects? Well, again, that's just getting familiar, right, with the force of gravity. We know anytime there are two objects, the force of gravity would be g and then mass 1, mass 2, divided by the radius, the distance between them squared. Right? Keep in mind g is our universal constant, so g is that 6.67 times 10 to the negative 11th, which is always on your table of information. And then m1 and m2 would be the two masses in terms of kilograms, and r would be the distance between the centers of mass. Right? So if I have two objects, it'd be the distance from center to center. Right? So anyway, make sure you're pretty comfortable with that. How do you find the acceleration about an object, or about the Earth or something like that? So if I asked you, just instead of finding the force of gravity, just find the acceleration of gravity. Well, the key there is it's like starting with force. We know force is mass times the acceleration, right? So if we set that equal to the universal force of gravity that we just saw, we can see that this would be mass times gravity equals the universal constant times m1 times m2 all over r squared. And obviously if we look at this equation, one of the masses is going to cancel out. So g is equal to my universal constant times mass 2 divided by r squared. Right, so the biggest question that you do need to make sure you're thinking about is which mass cancels out and which one remains in the equation. And in fact, the mass that cancels out is the mass of the object. Right, so if I'm thinking about the Earth, so here I have the Earth, and then in order for me to have a force, I have to have another object in close proximity to the Earth, right? So I have an object on the Earth's surface. Well, there would be a force between those two, but the mass of that object would cancel out in the calculation for the acceleration. So the mass that I need is the mass of the Earth, and the radius that I need, the distance that I need, would be the radius of the Earth. So make sure you are kind of comfortable going back and reviewing this skill that we've seen before. But anyway, like I said, hopefully this is nothing new and nothing too bad. So a few definitions I did go ahead and throw in here for 6.3. You every once in a while see them reference the inertial mass versus the gravitational mass. And really, those are both representations of the exact same mass. And so that's where this can be a little bit confusing, is both of these are just mass. They're just m, right? So both the inertial and the gravitational. The inertial and gravitational descriptions really are just giving us an indication of how we found the mass. So an example of the inertial mass would be using Newton's second law, which is force equals mass times acceleration. Right? So if in an experiment or in a design or something of that nature, if you were pushing on a box or on a crate with a certain force, and from exerting that force you were able to measure the acceleration, right? So you could use a stopwatch and measure the acceleration to be whatever. So if you push a certain force, find the acceleration, and then use those to calculate the mass, then that would be an example of the inertial mass, right? So if we were to use an experiment like that, again by taking advantage of Newton's second law, that would be what they would refer to as the inertial mass. The gravitational mass, on the other hand, is anytime we're taking advantage of the universal law of gravity to find the mass, right? So if I had two objects in close proximity, whether one is something like the Earth and the other one's an object or whatever it may be, but if I had two objects in close proximity and I know that they exert an equal and opposite force of gravity upon one another, then the gravitational mass is just going to be, again, the mass that we would calculate by using our universal formula for gravity, our universal equation for gravity, right? So if I were to use this equation to help find the mass, then that would be an example of the gravitational mass. So again, the confusing thing is they're both the same mass. It's really describing the approach that we use to get there. So I do want you to be kind of familiar with those terms. If they ever ask you to find the gravitational mass, it means you should use the universal gravitational formula. If they ask you to find the inertial mass, then we should probably just start with forces and see if we can find the net force and the acceleration to find the mass. So example 1, a conceptual example here, right? And so go ahead and read through it if you haven't already done so, and maybe try this on your own. But we've got a binary star system which has two stars. The mass of star 2 is twice as big as star 1 compared to the force of star 1 on star 2. The magnitude of the force on star 2 on star 1 is. And the key concept here is, regardless of the size of the two masses, the force of gravity between those two masses is always going to result from both of them, right? So the force of gravity of one on the other one is always going to result from the universal constant and both of those masses anyway, right? It's going to result from both masses and the radius between them. So again, the key concept, the conclusion here is those forces, those masses will always exert the exact same force upon one another, right? So the force of gravity in between those two are always equal and opposite, because for either one we require both masses. So again, the force of gravity is always equal and opposite. It's the exact same size. The force on star 1 is the same as the force on star 2. And it is a very key idea, and it's one to make sure you guys are all pretty comfortable with, but hopefully nothing too tricky, right? It does involve both masses, and so therefore the force is equal and opposite. This is also a lot like our collisions. We know in any collision, or really in any interaction, there's always a pair of equal and opposite forces. The same thing is true here, right? So as you're standing on the earth, we know that the earth is pulling down on you with a certain force, right? But you are also technically pulling up on the earth with the same force as well. The only reason we don't notice that force on the earth is much, much bigger. Okay, so example 2, probably a pretty easy example if you guys want to just try it on your own, but find the acceleration of gravity exerted by the earth on a satellite that is placed into orbit this high above the earth's surface, right? So they're asking us just to find the acceleration of gravity and not the force of gravity. And you'll notice they didn't give us the mass of the satellite, so we wouldn't be able to find the force of gravity. But that's okay. So using my acceleration of gravity, again, to find g, it's just going to be the universal constant times the mass of the earth divided by the distance squared between the center of the earth and that object. So the only thing you do have to be careful about here, so here's my earth. I'm going from the center of the earth all the way to the height of the satellite, right? So I need the total distance to be representing my r. Okay, so again, I've got the mass of the earth. They just flat out give that to me, which is good. I've got my universal constant because I always have that, and then I just need to find my r in terms of that total distance, right? So the biggest key here, the biggest concept here is r is going to be the sum of the radius of the earth and the altitude above the earth, right? It's going to be the radius to here and then the height above the earth's surface as well. So 6.37 times 10 to the 6th plus the additional altitude of 35,900,000. Right, so that would represent my total radius. So then, as a matter of just plugging this in here, so if you want to calculate that first, you certainly can. I'm just going to show the whole thing plugged in. So again, my universal constant, 6.67 times 10 to the negative 11th. The mass of the earth they give me is 5.98 times 10 to the 24th. And again, I'm using the mass of the earth and not the satellite. And then I'm using this total distance, which again, you can either calculate ahead of time or just do it like this. But I'm going to use this total distance, this total height, if you will, and then make sure that I do square that distance as well, right? So it's not anything too tricky. Just make sure you're careful with plugging this in, and we should get the acceleration. Obviously, it should be less than 9.8, right? We know 9.8 would be at the surface of the Earth, and if the radius increases, then obviously this value should decrease. So we know for sure it should be less than 9.8. And in fact, it's significantly less than 9.8. Because that altitude was so high, this ends up being about 0.22 meters per second squared, right? So the acceleration due to the Earth at that altitude is about 0.22 meters per second squared. So anyway, be pretty comfortable working through an example like this. Like I said, really nothing new here, so hopefully just a review over stuff that you guys are already pretty comfortable with. Okay, so last year in Physics 1, we worked with the assumption that planets followed a circular orbit, which allowed us to simplify situations, right? We were able to find the period and the orbital velocity. So I did throw in just let's go back and make sure we know these equations, know where these equations come from. So the key idea with orbit, right? So here's the Earth, here's the satellite orbiting around the Earth, and pretend it's a circular path, although obviously not quite, but close enough. Okay, so we've got the Earth, we've got the satellite orbiting around the Earth in a circular or a roughly circular path. Well, in order to move in a circular path, what force do we have to have? We have to have the centripetal force, right? We have to have a centripetal force that's directed towards the center of the circle. And remember, the biggest key with centripetal force is centripetal force always has to come from something else. So in this case, when we talk about orbit, what's the only thing that can be providing the centripetal force? Right? Again, centripetal force is not its own force. Think of it as the net force. Well, as we go around in a circle here, the only force that's acting between the satellite and the Earth is the force of gravity between them, right? So the centripetal force has to be coming from, it has to be equal to the gravitational force between both the Earth and the satellite. So my centripetal force, which is mv squared over r, needs to be equal to, again, the universal force of gravity, so g m1, m2 over r squared between the two bodies, between the two objects, right? So then cleaning this up a little bit, I can solve for the orbital velocity. I can solve for the velocity needed. So the mass of the satellite would be the one that cancels out, which means the mass of the Earth is the one that's needed over here, right? One of the radii, one of the distances there can cancel out because it is the same distance from center to center. So I end up with v squared equals g times the mass of the Earth over the total distance, over the total distance r, and then square rooting both sides. I get v equals, obviously, the square root of gm over r. So that is my equation, that is my approach for finding the orbital velocity. Right? So on the questions where they ask us to find the orbital velocity, if it's following a circular path, then that's the approach that we take. Right? So we just plug it in and go from there. What about if they ask us to find the period? Well, to find the period, the easiest way to remember to get there is, right, if it's moving around in a uniform circle, if it's moving around in a circle, the period represents how long it takes to complete one cycle. Well, if it's moving around at a constant speed in a uniform circle, just think of this as v equals delta x over t, right? How far does it have to go as it revolves once around the Earth? Well, its distance would be 2 pi times r, right? So the velocity, which I just found, the square root of gm over r, would be equal to 2 pi r over t. So I've got gm over r equals 2 pi r over t. So then if I want to solve for the period, I just have to solve this equation to get t by itself. Right? So if I do a little bit of multiplication here, if I multiply t and then divide that over, I would get 2 pi r divided by this beautiful radical. And then obviously at this point I could do a little bit more to clean it up. And if you recall, this is what gets us down to the equation that we had last year doing some algebra. And I get r cubed, the square root of r cubed over gm times 2 pi. Right? So this is my equation for the period. Again, being comfortable, hopefully, where that equation comes from. Right, so definitely some things to work through. Like I said, if you do have any trouble with this type of stuff, let me know, and we can certainly go back into that a little bit more. Okay, so let's now look at what actually happens, right? So we know that in real life, objects don't rotate, don't orbit in perfect circles. In actuality, they follow slightly elliptical or more elliptical orbits than obviously perfect circles. So what we'll start to look at really with the rest of this first section are Kepler's laws for elliptical orbits. Right? So the first law is all planets do move in elliptical orbits with the sun at one focus, and we'll see what that means here. A lot of this is going to come down to the geometry of an ellipse, which I will help you guys review if you need it. The second law, the radius vector drawn from the sun to the planet, sweeps out in equal areas in equal time intervals. Again, we're going to see exactly what that means, so don't freak out when you don't quite understand what that means right now. And then finally, the third law, the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Again, very wordy and probably some unfamiliar terms or uncomfortable terms for us right now, so don't freak out when you see this. We will work our way through this. These laws are very important, but they're not as bad as maybe they sound like they're going to be right now. It just takes us getting familiar with the geometry of an ellipse and seeing how that can be used to help us with these elliptical orbits. So anyway, I'm going to go ahead and stop the first part of the video here, and then we will delve into more of these explanations in the second part of this set of notes.